Our second speaker this morning is Johannes Broedel from ETH. He's going to tell us about recursion and doubling for scattering amplitudes.
Thank you very much. I'm actually very happy to be back at an in-person conference, and I'd like to thank for the invitation to talk about recursion.
Are you mute still? Sorry.
Excuse me. This is good. Thanks. So again, thanks for the invitation to speak here. And I'm very happy to be back at a conference in person. I'll talk about recursion and doubling for scattering amplitudes. We've been hearing something about very large structures, space-times, infinite future, and I will talk about very small objects. And I'd like to take a geometric viewpoint here. So if we talk about scattering amplitudes, these are objects which can be calculated in any reasonable quantum field theory or string theory. And of course, they are observables carrying the symmetry and properties of the theory, and perturbative objects. That is, I will only talk about the perturbative objects here. And of course, they can be converted into cross sections, which can be measured at collider experiments. And in some sense, they are the link from theory to experiment, maybe the most straightforward one. I want to compare and talk about scattering amplitudes in QFT on the one hand side, and these are usually calculated using the Feynman formalism, while the scattering amplitudes in string theory are calculated as worldsheet correlators in a conformal worldsheet theory. The first comment I'd like to make, and take that as a starting point for the discussion, is that taking the field theory limit of a string amplitude, that is gaining the result for a Feynman calculation in a limit as a limit of a string theory amplitude, is at least cumbersome, if not impossible in many situations. Now, let us talk about what is structurally happening in a quantum field theory. So first of all, the Feynman formalism is believed to be predictive, and believed is only here because there is no proof actually that this will yield the scattering amplitudes we measure, but it's of course amazingly well confirmed, and there is probably nobody doubting the validity of the formalism. We have a perturbative expansion, which is a loop expansion in the diagrams, and the integrals, they need to be regularized, and of course one is usually using dimensional regularization or something similar, and one will obtain these amplitudes as an expansion in some dim-reg parameter. And this regularization of the integrals is usually very difficult, and more importantly, it is done on an integral by integral basis. That is, you calculate a particular amplitude, and then you find a perfect regularization for that integral or class of integrals. And of course, there is an industry trying to understand the mathematics behind these Feynman calculations. There is the outer space, which is a way to address the graph operations you can do with those Feynman graphs. There is tropical geometry. You can take kinematical limits. There's that's only a small part. There is a plethora of different methods. On the contrary, scattering amplitudes in string theory, they are delivered or calculated as correlators on a pseudo worldsheet. Again, we have a perturbative expansion. It's a genus expansion, and we get a second expansion here as well. For the Feynman, we have the loop expansion from the diagrams and the expansion in the parameter for dimensional regularization. And for the string theory, we have the expansion in the inverse string tension and in the genus. And the scattering amplitudes in string theory can usually be split into a field theory part times a string correction. And it's those string corrections I will actually be mostly concerned with. Now, this is the basic approach. It's the bottom-up approach. You calculate your amplitude, but of course there's alternatives and shortcuts, and people have thought about how to ease the calculation of these amplitudes. And the most successful concept might be collected in the word analytical constraints. So one can try to have a shortcut by determining scattering amplitudes from these analytical constraints. That is, one knows what is the soft behavior, what's the collinear behavior. There are some symmetry properties that might be a theory with color. And there is PCJ identities, which is again a color implied identity. PCJs for Banca-Haskell-Johansson. And there is a lot of different bootstrap approaches. There is polylogarithms with the symbol alphabet. And there is also concepts like looking at the results and deriving constraints on transcendentality. There's Galois theory determining some coefficients in high loop scattering amplitudes, and Kutkowski rules and unitary cuts are there as well. I would like to frame all these concepts in two main words here. The first one is recursion. That is, one will reuse results from previous, easier or smaller calculations. And most famously, there is in Hennig-Fossow-Young-Mills the Park-Taylor formula, which is a very, very simple implementation of a recursion. But there's also BCFW for Broedel, Krashazo, Feng, and Witten recursion, and CSW, many more. More general for gauge theories, there's the Behrens-Rehler off-shell recursion relations, together with Kutkowski rules. That was something which was used already early in the 70s and is now actually the backbone of most of the numerical Feynman calculating mechanisms. And then there is many recursions which rely on a geometrical picture for integrands of scattering amplitudes. That is, objects before you integrate over the loop momenta. And there's also a string version of the Behrens-Rehler recursions. And the second concept I would call doubling or double copy relations or KLT relations. So let's just refer to doubling. There is field theory double copy relations which allow from a gauge theory point of view to derive gravitational amplitudes by a squaring and adding squares procedure. This is actually related to the existence of Banca-Haskell-Johansson identities. In addition, we have the KLT relations, very old, from 85, 86, Kawai, Levan, and Tai, which relate open and closed string amplitudes. And this is again a doubling, as we will see in the future. I want to mention that in the current approach to gravitational waves, there's also a lot of double copy involved in calculating the post-Newtonian approximations for the wave form of the mergers of neutron stars. And I also want to say that some of the classical symmetries of the closed string amplitudes can be actually attributed to that square amplitudes, squaring the gauge theory amplitudes. So the status is that recursion and doubling ease and enable many of the calculations which have to be performed, but in no way they are the most important concepts. It is rather that in very particular scenarios, you use them, and then if it's not possible, just refer to Feynman and do your honest Feynman calculation. There is some very symmetric scenarios where you can actually determine all scattering amplitudes with recursion and doubling. I would like to discuss what I believe is a versatile formalism in order to model general recursions. And it will be something which I hope to be applicable in string theory. Actually, I know it's applicable in string theory and in field theory, hopefully as well. And I suggest a similar setup for the doubling. Now, what would you dream of if you want a mathematical approach to recursion relations? The essential things, and there the first point is the most important, I'd like to model a recursion as a smooth process. That is, I'd like to have for this recursion an interpolating parameter, something which in two certain limits will actually connect between the two situations. Say you have a 4-point amplitude and you have a 5-point amplitude, and I want a mathematical formalism which, like a shifter, allows me to smoothly interpolate between those two. Why do I want this smooth interpolation? Because at the boundaries of the parameter space for the interpolating point, I will get some information about the regularization of the objects I'm considering. That is, I want to understand recursion not only as a process of getting a result by, say, multiplying a 4-point amplitude with a certain object in order to get the 5-point amplitude, but at the same time, I want the regularization procedures to be connected in a mathematical framework. And I want to set up which works for integrated expressions, not for integrands, but for the full amplitude. What would be also nice is if one would have a geometric interpretation and some control over on-shell or off-shell recursion. And finally, the last point, one should find a way to express field theory amplitudes in a way that they can be accessible as limits of string theories more easily. How to model this type of thing? Let's take a short detour and look at what is done in the honest Feynman calculators world. So what one does, one starts with a Feynman integral, one uses Feynman parameterization, that's the standard thing, first place. One will obtain the so-called semantic polynomials, that is a formalization of denominator and numerator structures of the integrands of those integrals. And then one will single out a set of so-called master integrals, which is nothing else as a cohomology. You select a basis, which is a basis with respect to identities between these integrals. Now, in the next step, you would write down a differential equation, and there is an algorithmic way to obtain these differential equations. These equations are for most known cases of Fuchsian type, and you solve it, you obtain solutions, you continue analytically, and then you calculate the fundamental group or the monodromy group associated to the algebraic variety, which corresponds to the differential operator. And it is clear that the solutions for this Feynman integral, or this class of Feynman integrals, can be written as iterated integrals with respect to differentials, which transform under the fundamental group in a nice way. This is something which has been shown for many examples during the last couple of years, and this is, from a very distant point of view, the way how to do that. Now, getting back to this setup, I'd like to establish something like that actually exists for string amplitudes already. So for string amplitudes, we have no trouble defining cohomology. We know that there is a set of master integrals. These are iterated integrals, and they are Selberg integrals. They have been defined by Selberg already in the 60s. And I've just written down an example. The basic idea of, or the basic structure of a Selberg integral is that it has an exponential factor, which is here this exponential of the logarithm of two geometric points, two insertion points for the string worldsheet, and it comes with the Mandelstam variables Sij in the structure. And this is somehow, it's called a Selberg seed. It is something where you can take derivatives of. And then together with this Selberg seed, there is a set of differentials. Here it's dx over xk plus 1, ik plus 1. So it's dx over a difference of the two insertion points, the most basic integral you can imagine. And this interpolation I would like to describe is done with an extra point. That is, I will take a fake extra insertion point with a fake extra vertex operator, and then use that as the parameter interpolating between the two situations I want. Differential equation has poles, and at the end of the interval, I will get the regularized expressions I want. I will show an example in a minute. Actually, I will show two examples. I will show how this kind of recursion works at tree level, and that is the implementation which is analogous to the Park-Taylor formula for Boolean amplitudes. It's the same thing for string theory, but in this situation, it delivers the full string expansion at tree level. And I will show that this also works straightforwardly to calculate one loop string amplitudes. Now, first example, this open string recursion refers to basically removing or adding a leg. So there is the 4-point amplitude, which I've sketched here as a worldsheet, and then I would like to add a 3-point string vertex, and this could be also here or here or here, but of course I only want to add one of them and obtain a 5-point amplitude. And how is that done? It is done with an extra geometry parameter x3. This is the extra point, and it's called x3 for a particular reason I don't want to comment on. Just it is you would have insertion points x1 to x5, and it's very convenient to choose x3 as the interpolated parameter. And then I have a set of integrals that are integrals for the 4-point amplitude with an extra point. So this S0 is a basis for the cohomology I'm looking at. And I have a equation, which is an equation of Knižník-Zamolodchikov type, very well known in conformal field theory. This equation has two poles for x3 equals 0 and one for x3 equal 1. And it comes with two coefficients, which one can construct, which have a matrix representation. And it turns out that taking appropriate limits of these integrals as 0, one can indeed retrieve the information about the endpoint and the n+1 point amplitude. So there's a certain regularization at the x3 goes to 0 point. So once I approach that limit, I have to deal with the divergent integrals here. But this one, C0, is a finite regularized boundary value, and it can be shown to contain the 4-point amplitude, and C1 is a regularized boundary value, which can contain the 5-point amplitude. What's happening geometrically here? We are considering a disk amplitude, which I would like to show here as half of a Riemann sphere. So just take the real line, which is drawn here in red, and this parameter x3 is hovering between 0 and 1. So on this lower quarter here, if I take the limit of x3 going to 0, then all the insertion points are squeezed in a very tiny little interval. And what happens is that x2 and x5, which are at 1 and infinity, appear to be both infinitely far apart. So they basically reconcile into 1 point. On the other hand, if I take x3 going to 1, then I will just recover the regular string amplitude for 5-point tree level. And there's a theorem by Drinfeld telling that these two regularized boundary values are related by an object called the Drinfeld associator. And the Drinfeld associator allows to multiply the one boundary value and obtain the other one. Now, a short example. There's the differential equation again, and there is two matrices with Mandelstam variables. They are linear in there, and the Drinfeld associator can be expanded into a series, which is a generating series for zeta values, and you will see some commutators of these matrices, which you can calculate once they are there. And taking that object and multiplying with C0, you will recover this kind of expansion here, taking just one component of the appropriate vector, which is nothing else as the expansion of this very well-known Veneziano amplitude. So there's an algebraic way of getting n-point tree-level string amplitude to any order in alpha prime. The alpha prime is hidden in each power of this Mandelstam variable here. The same thing actually works at loops. You can also ask the question, is there a similar equation for one loop string amplitudes which does the job? And the answer is yes, there is. You take again a basis vector of one loop string integrals. Here it will be a 6-point amplitude at tree level, interesting, in the limit, and a 4.1 loop amplitude on the other. So you take this one loop vector, you write down a differential equation. Now this G21 is the genus 1 analog of the 1 over xi minus xj over the analog of this inverse distance. And again, there is some coefficients E here for each of the poles. And once you have this equation, you can again derive representations for these matrices. This equation is called the elliptic KZB equation. Here, KZB is for Knizhnik, Zamolodchikov, and Bernard. And the punchline is, if you again consider Z2 as an extra point, you can, in the two limits, Z2 goes to 0 and Z2 goes to 1, obtain all one loop string amplitudes. However, this time they are not obtained from lower point one loop amplitudes, but from tree level. So if you have a 4.1 loop amplitude, you somehow cut it open and you get a 6-point tree level amplitude. This is like taking a unitary cut, however, in a smooth and geometrically nicely understood way. For the one loop amplitude, you would consider an annulus or half a torus, and the Z2 parameter would do what the X3 parameter did in the tree level setup. It would squeeze all the other insertion points into a small interval, and by this make the, let me talk about the torus or the half torus, very, very thin and very, very, actually have a very, very long throat, which can then be cut. I will show a picture in a minute. On the other hand, if you take Z2 going to 1, you will get the one loop amplitude. And again, there is an associator, the KZB associator, which if you multiply it with a regularized boundary value, so regularization is happening again at the two sides of the interval, you will get the one loop amplitude. I won't show an example because it is rather involved, but it is simple. It is just linear algebra, which is extensive, and the computer will that do for you. And one gets the 2.1 loop result, which consists of zeta values, and there is some elliptic multiple zeta values. That is a genus 1 analog of zeta values. It's actually not values, but it's a function on the elliptic curve with a parameter tau. But this is the right objects to talk about one loop string amplitudes. And the message here is you can actually get this result. Not only this one, but all other known one loop results. I'd like to ask, what is the geometry behind here? So if we take this Z2 parameter and we shift it around the annulus on this outer boundary, then we are doing the following thing. Let me actually start with the Riemann sphere. And this Riemann sphere should, for the start, have two additional insertion points. So there will be some insertion points which I choose to be on the half of the real line. And then at the North Pole and the South Pole, there will be additional insertion points. And now I can grab these additional insertion points, pull a little, and actually change the torus and make these two insertion points in a cylinder-like shape, or the whole thing, and then connect them and glue them and get the torus out of here. So I'm talking about the torus. The concept I told was only about half of the torus, but the geometric way is precisely the same. Now, this is a very smooth transition, and the two additional points at the tree level or genus 0 amplitude, they will disappear in favor of changing the topology of the surface I'm calculating the amplitude on. there is a even more clear relation. The Mandelstam variables are related in a certain way, but this works. So I can get all string, open string, one loop amplitudes from tree level amplitudes, and we have that recursion. Now, question, can a similar setup that is a geometric setup with an interpolating parameter done for doubling? The answer is yes. The idea is the following. You take, again, the Riemann sphere, and you take the real line, and you introduce a parameter which will take the real line and interpolate between just the real line, and then blowing it up to the whole complex plane, describing a Riemann sphere after all. So the closed string amplitude is for the Riemann sphere, and the open string amplitude is calculated about over the boundary of this. So you can interpolate between these two. And in order to really find what the KLT relation advises you or tells you what it is, you will have to think about the combinatorics of these points. You have the points on the real line, you blow it up, then there will be points on the Riemann sphere. And after all, this whole construction relies on a certain succession of traversing these points which are not fixed by an SL2 symmetry. So on the Riemann sphere, you always fix 3 points, a position of 3 points if you calculate the amplitude. And what is left is n-3 other points. And the famous n-3 factorial basis for some gauge theory amplitudes or the string amplitudes is precisely caused by the n-3 factorial ways of traversing the remaining points on the Riemann sphere. One can show that it works for 4-point. For the general formalism, there is one limit question which is not completely settled yet. So the calculation gives the right result, but in the proof there is a little gap missing. We're working on that one. In order to wrap up, I would like to go back to field theory. That was the starting point. I wanted a formalism which would allow me to calculate scattering amplitudes recursively or by doubling with a smooth parameter interpolating between the situations I want. And after having shown that this works for string theory, let us think about where could this happen easily in a similar manner in field theory as well. The first thing which comes to mind is the multi-Raggi kinematics. That is where you have only a very limited class of amplitudes, a certain kinematical regime where you have almost no transverse momenta in scattering. And the class of objects is again iterated integrals, it's single-valued polylogs, and it's very likely and to find a similar description here. So a description not in terms of finite integrals, but here it is the BFKL equation, which can be mapped to the Cauchy-Samologikov type equations. And there's, for example, the Y systems, which allow you to derive an expansion for a particular amplitude with single-valued multiple zeta values. And single-valued multiple zeta values, again, are represented by single-valued polylogs, a very restricted class. It's very likely to also find recursion there. And if you're thinking about string theory, what I showed you for the tree level and for the one loop is something which can be generalized to a higher genera as well. You will have to think about how these surfaces actually degenerate, but there is a lot of mathematics known. You will need Siegel modular forms. It's higher groups. It's not SL2 anymore. There's the Arachelov-Green function, and a lot of techniques are known there. It's more a combinatorial problem, writing down what happens. Finally, the geometric setup for blowing up the real line to a Riemann sphere will also work for taking the annulus and completing that into a full course. Now, let me end with an outlook slide and further thoughts. First of all, this geometric language with a smooth interpolation between two different amplitude setups is very natural in string theory. And it's natural because here we have a surface and we can take directional derivatives. We know how regularization works. The buzzword here is tangential base point regularization, a concept very well known for mathematicians dealing with polylogarithms or other iterated integrals on higher Riemann surfaces. I want to emphasize that this language is fundamentally different from the Feynman language because it is just one geometry, the geometry of Riemann spheres with marked points, which is responsible for one amplitude. And thus, this geometric picture allows to this interpolation process. Most of the Feynman-based recursion relations, they will just have an effective theory which tells you how to relate one end to the other end. There will be no differential equation governing that kind of process. I already said the modular spaces of Riemann spheres with marked point and the corresponding degenerations are very well understood in mathematics. There is actually a complete hierarchy how to deform higher genus Riemann surfaces with marked points to lower ones by connecting, by sewing these points in the same way as I showed with the torus. For an immediate goal, it would be amazing to actually find a representation of scattering amplitudes in any Four-Super-Young-Mills theory for which all the known recursions show up as particular limits. This ought to be not a Feynman type description, but rather a description in terms of iterated integrals. And once one can frame scattering amplitudes in any Four-Super-Young-Mills theory as iterated integrals, then immediately recursion in the kind I described it for the string amplitudes would be known. Finally, this idea comes from a mathematical or from actually two mathematical setups beyond the Riemann spheres with marked points which are there. The first one is topological recursion. Topological recursion is a concept where you actually give up, of course, the geometry and you just ask the question, what kind of algebraic objects can be deformed into each other once you deform or you topologically connect surfaces of various genera. Gaëtan Borot and Bertrand Aynard have been coming up with a topological recursion setup, and this setup actually shows precisely the signs and signatures and mechanisms which we have with this geometric string theory recursion setup. And there is also recently been some work on so-called homotopy Lie algebras, and homotopy Lie algebras will be providing the algebraic setup governing the matrices E0 and E1 and further matrices in the matrix representations for the recursion. So in the long run, I hope that such a geometric recursion relation can be established also for many, if not all, quantum field theories. So what one would dream of is a differential form defined on a suitable manifold, which would encode the information about the theory and allow with an interpolating parameter, which might be interpreted as an extra point or an extra leg, which would allow using that formalism to predictively derive recursion relations for any theory if they do exist. And the benefit here would be that you would get information about the regularization from the formalism right away. Thank you very much.
Thank you very much for a nice talk. We have time for some questions. Yes.
So you have the Knight Molotov equation, and for some because it's really much iterated into mathematically. But Is there a conceptual explanation why you get some? I mean,
Yes, it is.
It's tempting to think that there is a component filter under it. But that's not the original.
That's of course an explanation, but it's not the reason. The reason is that the string theory amplitudes we're considering are very simple amplitudes. If you would do what we did for the Feynman integrals and calculate the monodromy group of the differential equation, or of the monodromy group underneath the polylogs which constitute the string amplitudes, then it would just be SL2 with two poles, 0 and 1. And if you start from 0 and 1, the answer to the question, what is the easiest equation you can write down, is precisely the Kniznik-Samologikov equation. So it's the most trivial cut you can actually have on your polylogarithmic surface. And that's the reason it shows up. It's actually the same reasoning which leads to the Kniznik-Samologikov equation for the elliptic surface.
There is also, I mean, for example, Dirk Primer, he has been trying to get this equation. Is this related to what you do?
It is not related to what it does. Okay, so I mentioned, and I did not put all the references in here, the outer space approaches. And outer space is the approach put forward by Dirk Kramer and Karen Vogtmann and several other people. And their point of view is that they take the Feynman graphs and they deform the Feynman graphs. That is, they shrink operators, or they join vertices in order to form additional loops and bubbles. And they ask the question, what is happening with the associated Feynman integrals? My point of view here is that Feynman integrals as a language bear a lot of divergences and mathematical complications, which can be remedied by finding a formalism which is rather defined on a surface, on a two-dimensional manifold, rather than having Feynman diagrams which have just lines and no geometry, but just topology.
Another question?
Thanks very much for the talk. You mentioned that one of the motivations of having this interpolating model is continuously connecting different regularizations.
Indeed, yeah.
Do you have any kind of new results on non-trivially linking two different regularization schemes with different loops or different number of points?
So the two examples I showed, I would still call them new results. So these string setup for one loop was something I did with my PhD student, Andre Kaderle, just before Corona hit in, and now we can algorithmically, algebraically, without regularization, calculate all the one loop string amplitudes. That is something which took quite a while to establish. For new results, I would refer to the doubling slide I had here. That's preliminary, that's work in progress. And also for the multi-region regime I mentioned, I'm working with a master student and other people on establishing a recursion in the way I described it for this class of amplitudes. I would hope that if one, for example, thinks about the amplitude setups we've been hearing about, say, in an ADS CFT setup, for example, in Fernando's talk, that this type of amplitudes will actually also be governed by a similar recursive algorithm. So it is simple enough in the result to be accessible to that kind of formulation. It's just probably very hard to define or to find the appropriate differential form on the surface, on the Riemann surface with marked points in question. But thinking about calculating field theory amplitudes from a string perspective is precisely what has been done. And so in between the lines in this talk, I want to suggest to think about field theory a little more in terms of a surface formulation.
Questions from the online audience? Don't see any. So maybe let's thank Johannes again.